The James Webb Space Telescope taxed the scientific and engineering communities before, during, and after its launch. However, the $10 billion gamble is beginning to pay off as the Space Telescope has started showing us the stuff it is capable of with the latest image of the cosmos that is sent back to the Earth. In fact, even at this stage, the JWST is already sending back intriguing images. And in this video, we will show you how NASA has rapidly got to this stage where the JWST has captured an unknown object in space. How far did you go in your riskiest adventure? If you ask NASA, the answer is literally about 1 million miles, and it was at the cost of a whopping $10 billion. Basically, everything about the JWST had to be invented to tackle the unique problems it would face at its location, and perplexingly, the inventions added to the complexity of the telescope. For instance, the engineers had to develop a way to cool the telescope to ultra-low temperatures to enable it to work without interference. The solution was a series of 5 sheets of special materials acting as a heat shield. But then the 5 sheets had to be precisely placed for them to work. But that was not the only problem posed by this solution. Each of the sheets is as large as a standard tennis court, which complicated the launch since, obviously, there is no rocket in operation that could take the heat shields. The solution to the problem caused by the solution to the cooling problem was to fold the sheets during launch and unfurl them during the trip to its permanent orbit. That was a scary proposal as the JWST quickly left the range of distance within which humans could approach it to fix any problem. The reflecting mirror had to be handled the same way for the same reason, it just couldn't fit onto any launch rocket. The solution was to break it up into 18 different hexagonal mirrors and fold it up during the launch to orbit. Thankfully, the uncertainty of the launch is behind us, and the task at hand for NASA is to align and calibrate the different components so that they can all work together and as intended. The good news is that even though the alignment process, which involved fine-tuning the positions and inclinations of the 18 segments with a nanometer scale precision, is not yet complete, the JWST mission is already producing images that take the scientists' breath away. But how is the alignment done? It contains some mind-blowing engineering. There are 7 small motors fixed behind each of the JWST's 18 slightly curved hexagonal mirrors. Their function is to move and reshape the curvature of each segment so that all 18 can act as a single large mirror. 6 of these motors are grouped in pairs, equally distanced and located around each mirror segment. These are used to move the mirror. However, the 7th motor is at the center and is connected to the mirror's 6 corners with struts. This motor can adjust the tension of the struts, which optimizes the curvature of that mirror segment. The motors are so sensitive that they can precisely move the mirrors to within about 1/10,000th of the diameter of a human hair. This precision to within a fraction of a wavelength of light is crucial for scientists to obtain high-quality images from the JWST. NASA scientists used a mathematical analysis called phase retrieval to study how the movement of each individual segment changed the sharpness of the final image. With this info, there were 2 crucial tasks to complete before the segments could function as a single monolithic mirror: coarse alignment and fine alignment. In coarse alignment, the mirror segments were moved up and down until they aligned to form one giant mirror. However, there were still minute alignment errors that needed to be corrected to obtain the best possible image. This is where the fine alignment occurs. In this step, instead of moving the mirror segments, the small optics inside NIRCam moved instead. When the telescope is pointed at a star, the light from the star first hits the primary mirror, in which the individual segments are now aligned reasonably well. The light then continues its path through the secondary and tertiary mirrors inside the telescope and enters the NIRCam instrument. During the fine alignment, the optics inside NIRCam are very carefully adjusted until the star is completely in focus. The coarse and fine alignment steps are both repeated until the sharpest image can be obtained. The image released by NASA recently shows how a star looks when these steps are completed. Prior to this, NASA released a stacked image back in February. For this, each of the individual mirror segments was fine-tuned to create 18 sharp images of the star, but each from a slightly different vantage point. The 18 images were then stacked to produce a single image. When the mirror alignment process started in early January, the ground team trained the telescope on HD 84406, a star that scientists described as very boring in our Milky Way galaxy. The star, 100 times fainter than what can be seen with the naked eye, was chosen not for its scientific significance, but purely for its brightness and location. The star is located about 2,000 light-years away. At the beginning of the alignment process, the telescope was delivering 18 individual images of the star, with each of the primary mirror segments acting as a telescope on its own. However, the image released recently shows a bright, shining, amber-colored star emanating streams of light across the universe. Interesting than the star itself, however, is its background, revealing dozens of specks and dots, each a distant galaxy that was previously out of reach. These distant galaxies make Webb's first image a so-called deep field. Such photographs, focusing on small sections of the sky, aim to capture the most distant objects in the universe. Deep fields are a speciality of the Hubble Space Telescope, Webb's predecessor. Webb, however, will handily beat Hubble in its ability to peer into the depths. Showing its superiority, where Hubble requires weeks to obtain some of its best deep field images, the JWST will accomplish the same results within hours. But of course, the two observatories don't image the universe in the same wavelengths. Hubble is an expert at visible and ultraviolet radiation, and JWST uses infrared. The Webb telescope was designed to be up to 100 times more sensitive than Hubble, and that goal has not just been accomplished, but exceeded. Lee Feinberg, Webb Optical Telescope Element Manager at the NASA Goddard Space Flight Center, said in the last fall, NASA said it would know that the telescope is working correctly when it has an image of a star that looks like, well, a star. Now the JWST has produced such an image. He was excited that the optical performance of the telescope was absolutely phenomenal. The performance was as good, if not better, than NASA's most optimistic prediction. The mirror alignment was done with the help of the Near-Infrared Camera, or NIRCam, one of JWST's 4 scientific instruments. The remaining 3 are still waiting to be activated. They include the Near-Infrared Spectrograph, which will examine the light spectra from distant objects to learn more about their physical properties, such as their temperature and chemical composition. The Mid-Infrared Instrument, which is both a camera and a spectrograph that captures images in wavelengths the eye can't see, and the Near-Infrared Imager, or slitless spectrograph, a very precise instrument that will look for and investigate exoplanets. The next stage will take about 6 weeks and will be followed by a final alignment stage in which the JWST team will adjust any residual positioning errors in the mirror segments. The team is on track to conclude all aspects of optical telescope element alignment by early May, if not sooner, before moving on to approximately 2 months of scientific instrument preparations. Webb's first full-resolution imagery and science data will be released in the summer. In addition to aligning the mirror, the scientists had to wait for the instruments to cool down to extremely cold temperatures close to absolute zero. Since Webb is an infrared telescope and infrared light is essentially heat, any warmth emitted by the telescope and its instruments would dazzle the detectors and make it impossible to see the most distant objects in the universe. Many of the features also have redundancies built into them, which means if a system should fail, there will be another way to achieve the same objective. The JWST is a collaboration among NASA, the European Space Agency, and the Canadian Space Agency. It is named after former NASA Administrator James E. Webb, who led the agency during the Mercury, Gemini, and much of the Apollo space programs. So what will the JWST picture first when it is certified as ready? Unless you have the topmost clearance at NASA, you could only guess for now. Jane Rigby, the James Webb Space Telescope Operations Project Scientist at NASA Goddard Space Flight Center in Maryland, said the targets had been selected, but they remain a super secret. However, many other early targets for the observatory are public knowledge. During a news conference, Rigby confirmed that JWST's first year of science observations is already finalized. She revealed NASA received more than 1,000 research proposals from astronomers worldwide and selected the best ones, including those looking for light from the first stars and galaxies that emerged in the early universe only a few 100 million years after the Big Bang. Let's hear what you think of the early images of the universe captured by the JWST in the comments section below.